Good afternoon, dear colleagues. I would like to present my work, which is devoted to the application of the rock damage model to thermal oil recovery. I shall divide my talk in the following way. I would like first to say some words about the relevance of my work. In the second part, I will give a description of the steam-assisted gravity drainage model and the details of its computer realization. The third part will concern verification of the model. The next part considers the effect of damage-induced deformation and non-uniform steam chamber distribution along the horizontal wellbore on the oil production rate. Motivation. Thermal methods of oil recovery are accompanied by various geomechanical effects, which are presented in Figure 1. One of the key geomechanical effects is surface heave. Field observations show that the observed values of a surface displacement can vary from several millimeters to several centimeters, as it is shown in Figure 2. This effect can be explained as the development of shear failure, which occurs in reservoir due to the propagation of the thermal front. Moreover, shear failure together with microfracturing of the soil can significantly increase porosity and permeability and thereby magnify recovery factors. In this work, we will propose damage model which describes these effects in steam-assisted gravity drainage method of heavy oil recovery. According to this method, a number of horizontal wells are drilled one above the other, as illustrated in Figure 3. The upper wells are used for the injection of the hot steam, while the lower wells are used for the oil accumulation. Efficiency of steam-assisted gravity drainage is determined by the uniformity of the steam-saturated zone, which is called steam chamber. Schematic representation of the steam chamber is given in Figure 4. Under the influence of the hot temperature, the viscosity of the heavy oil decreases and it flows down the edge of the steam chamber into the production well due to the gravity. Accurate description of this method requires simultaneous consideration of the flow, thermal, and mechanical processes. Usually coupled THM processes in geological porous media are governed by the momentum, mass, and energy conservation laws, which are supplemented by state laws and constitutive equations. The aim of this work is to develop a mathematical model which takes into account main mechanisms of steam-assisted gravity drainage, which are reduction of the oil viscosity, gravity-based drainage, and shear fracturing, which enhances properties of the reservoir. The description of all processes accompanying the steam-assisted gravity drainage is a rather complicated problem. Therefore, the mathematical model of oil filtration is based on the following hypothesis. Pore fluid consists of the three immiscible phases, water, oil, and steam. The phase transition in the system is due to the temperature change, capillary pressure is neglected. Fluid flow is determined by Darcy's law, reservoir is assumed to be isotropic, and the strains are assumed to be small. The mathematical formulation includes mass balance equation for water, steam, and oil saturations, the condition of a fully saturated media, Darcy's law for each phase, and energy balance equation with convective heat transfer term and source term describing phase transition process. The mechanical part of the model includes the momentum balance equation, geometric relation, and Hooke's law for the effective stress, which are supplemented by constitutive equations for internal variables which describe damage accumulation. Numerical simulation was carried out in the finite element software Console Multiphysics. Solution of the filtration problem was based on the pressure saturation formulation with the total velocity. The equations 1-7 were reformulated and presented in a weak form. The artificial diffusion term is added to smooth the oscillations caused by the convection term. The final form of equations are presented by equations 13-14. The last step is the implementation of the obtained equations into Console Multiphysics using weak form PDE interface. The energy balance equation was reformulated in the form 15 and solved in the heat transfer module. The mechanical part of the model was solved in the structural mechanics module. Constitutive equations for damage accumulation were implemented in Console using coefficient form PDE interface. Efficiency of the proposed model and algorithms we will illustrate by numerical simulation of two laboratory experiments. The first experiment was taken from work of Huang and the others. They investigated steam chamber development in two cases. The first case was homogeneous reservoir presented in Figure 5a, and the second one was the reservoir with four parallel perspex plates acting as barrier layers, which is shown in Figure 5b. Physical properties used in simulation are presented in Table 1. Dependence of dynamical viscosity upon temperature is presented in Figure 6. Firstly, a preheating stage was simulated in both cases. When the temperature between the wells was equal to 70 degrees, steam-assisted gravity drainage was switched on to the formal stage. Figure 7 shows result of temperature fields obtained by numerical simulation together with temperature profiles obtained experimentally in case of homogeneous reservoir. We can see upward rise of the steam chamber and its lateral spreading along the up boundary of the reservoir. Figure 8 shows temperature distribution in the reservoir with barrier layers. It can be seen that in this case barrier layers impedes heating of the reservoir. The steam chamber first flows around barrier layers and only after this hits the interbedded zone, which confirms by experimental results. The second experiment is steam-assisted gravity drainage in heterogeneous reservoir. It is taken from work of Leo and the others. Sizes and geometry of the reservoir are given in Figure 9. Specific feature of this experiment is inhomogeneity of the reservoir in horizontal direction, which is reached by two different types of sands. Injection and production wells were placed in area with higher porosity and permeability. Properties of the materials are given in Table 2. Dependence of dynamical viscosity upon temperature is presented in Figure 10. Figure 11 shows temperature field obtained by numerical simulation and experimental temperature profiles after 600 minutes of steam-assisted gravity drainage. Figure 12 shows the corresponding steam chamber shape. The experimental results are in a good agreement with the simulation. Figure 13 presents oil recovery rate. Results of simulation show significant decline in oil recovery when the steam chamber propagates in the area with lower permeability and porosity, which confirms by experimental results. In laboratory experiments, we don't observe substantial surface heave due to the short duration of the experiment and restrictions imposed by experimental conditions. However, in the field conditions, oil recovery are accompanied by substantial structural changes of the reservoir, which affect porosity and permeability. We will investigate this effect on the basis of the damage model proposed at the Institute of Continuous Media Mechanics. It is assumed that the media can contain two types of the defects, volumetric and shear, which are modeled by a microscopic tensor S. Microscopic tensor P is obtained by equation 16 and defines additional structural strain induced by the initiation and coalescence of the defects. We will use this parameter as an internal variable describing structural changes in the material. We can obtain constitutive equations for volumetric and deviatoric parts of the structural strain tensor 2122, applying the thermodynamic formalism. To close the system of equations, it is necessary to define approximations for the partial derivatives of the free energy function f, which is included in equations 21-22. In case of the thermal oil recovery, compressive stresses are small, and the prevailing mechanism of the deformation is the shear dilation caused by the high temperature. According to the proposed model, this effect can be described as an accumulation of volumetric defects due to the increase in shear defects. Therefore, the approximation functions were assumed to depend on the first and the second invariant of the structural strain tensor. In the final form, equations 21-22 can be written as 23 and 24. We add these constitutive equations together with porosity and permeability equations 27-28 to our steam-assisted gravity drainage model to describe such effects as surface heave and concomitant increase in porosity and permeability. To demonstrate the efficiency of the proposed model, we will simulate steam-assisted gravity drainage in the reservoir containing two pairs of wells. Geometry is presented in Figure 14. Additional overburden layer of the soil was considered in mechanical part of the problem, while multi-phase flow was considered only in reservoir. Thermophysical properties correspond to Yarrigo oil deposit are presented in Table 4. Mechanical properties used in simulation are listed in Table 3. Specific feature of the simulation is accounted for the non-uniform temperature distribution along the horizontal well bore, which strongly affects the shape of the steam chamber. In general, simulation of steam chamber suggests consideration of the 2D profile. However, experimental results show that the temperature decreases along the horizontal well bore and steam chamber shape cannot be described by 2D profile. So in this work we have made an attempt to describe 3D shape of the steam chamber. Figures 15-17 demonstrate evolution of the steam, oil and temperature during 160 days of the heating, with account for non-uniformity along the horizontal well bore. These results are also taking into account structural changes described by p-tensor. Additionally, we have considered two more cases: uniform distribution with structural changes and non-uniform distribution without structural changes. In the last case, only thermoelastic strains were considered. Figure 18 shows volumetric part of the p-tensor corresponding different moments of time in case of the uniform distribution. Figure 19 shows values of the p-tensor at the same time moments but in case of non-uniform distribution. We can see that non-uniformity induces substantial qualitative difference in evolution of structural changes. Figures 20 and 21 presents increase in porosity compared to the initial value for the case of the absence and the presence of structural changes with account for the non-uniformity along the horizontal wellbore. On the initial stage, when structural strains are small, the shapes of porosity are similar to each other. Further development of the structural strains affects significantly spatial distribution of the porosity. Moreover, consideration of the structural changes allows one to obtain a rise in porosity by several %, while thermoelastic strains give significantly less values. Figure 22 presents results of the vertical heave obtained for the three cases: non-uniform distribution without structural changes, uniform distribution with structural changes, and non-uniform distribution with structural changes. As it can be seen, the single mechanism of thermal expansion couldn't provide significant values of the vertical heave. Structural damage defined by the proposed equation simulates additional contribution to strain induced by the rise in volumetric type defects microcracks due to the increase in the shear type defects microshears. Non-uniform distribution of the steam chamber induces non-uniform heave, as it is presented in Figure 22c. Figure 23 demonstrates oil production rate after the establishment of the interwell communication. Uniform distribution of the steam chamber doubles the results and gives the biggest value of the oil production rate. Therefore, the uniform model of the steam chamber development can overestimate the oil production rate, because in real steam-assisted gravity drainage process, when the steam chamber near the heel spreads laterally along the upper boundary of the reservoir, the steam chamber far behind the heel can be only at the vertical rising stage. As for the non-uniform distribution on the initial stage, when the influence of the structural strain is small, the oil production rates are slightly different from each other. When the volumetric increase in strain due to the evolution of defects is significant, the distinction between all models is more pronounced. Conclusion: three-dimensional mathematical model of multiphase flow in porous media was proposed. The model was verified by two different laboratory experiments. Comparative analysis of three different scenarios of steam-assisted gravity drainage has been carried out. Results have shown that estimated values of the surface heave and porosity are significantly lower when defect-induced strains are not taken into account. Accurate prediction of oil production rate requires consideration of geomechanical effects related to the structural changes of the reservoir, as well as non-uniformity along the horizontal wellbore. Thank you for your attention.